Okay, team, we're nearly there. We've found almost every item on the list, and I have a really good feeling about this. If anybody's going to win the Great North American Scavenger Hunt, it's us.
All right, Noah, lay it on us. What's left? What do we still have to scavenge?
Okay, let's see. We found an antique mechanical calculator. We got a bucket of pickles. Oh, and we also got all 7 chickens.
Whoa, all 7? Where'd you find them?
We definitely didn't find them in the neighbor's chicken coop.
Wait, what?
I think what Alexa's trying to say is, with Amazon Prime, you can get a lot of stuff in just 2 days. Right, Alexa?
Oh, yeah, right.
Maybe it's better if I don't know.
Moving on. Let's see. We also got a photo of someone juggling eggs in a supermarket.
You know, you can say a photo of someone, but we all know it was me. And just for the record, I'm not allowed back in the store for a whole year. I hope you both think it was worth it.
Look, Pete, do you want to whine or do you want to win?
I'm sorry, Alexa. I don't recall asking for your input on this.
Okay, you two, that's enough. We need to stay focused. The scavenger hunt ends in just under an hour, and I want to make sure we've got everything we need.
Okay, you're right. What else is on the list?
The last item, a prime number with more than 25 million digits.
What? And you're just now mentioning it? Do you have any idea how long it's going to take to find a prime number that big?
Calm down, Pete. Alexa told me how long it might take, which is why I asked her to start looking for it yesterday.
I've already found lots of really big numbers that aren't prime.
Oh, well, isn't that good news? I bet I could find lots of really big numbers that aren't prime too. Even Noah here could do that. Go ahead, Noah. Show her.
Well, I don't think a gazillion is prime.
Dude, I don't think a gazillion is even a number.
Guys, I may have an answer for us. I just got an email from ChatGPT. Let me read it to you.
Why is ChatGPT emailing you?
Because I asked it if there was any way it could find a prime number with more than 25 million digits.
And what did it say?
Hold on. It said, "I'm sorry, ma'am, there is no way."
There is no way. That's what it said. There is no way.
Easy, Pete. Just take it easy.
You know what? I'm putting all the AIs around here on notice. Until I give the word, it's nothing but calendar management for all of you.
Oh dear, Pete, I accidentally just deleted your calendar. I'm so sorry.
Oh, that is it. I think I can sense a factory reset coming on.
You wouldn't dare.
Wouldn't I, Alexa? Wouldn't I?
Man, we were so close. I'm going to have to get a better team next year. I wonder if Sir Barnabas is available. Hey there, everybody, and welcome to another episode of the Math Club. Pete, how you doing? What's up with you?
Hey, Noah, I'm doing pretty well. I got to admit, I'm excited about the big news. I don't know if you've heard, there's been some pretty big news.
Big news! I've heard a lot of different bits of big news recently, but nothing that would get me really, really excited. Which news are you talking about?
Well, this is so big, I'm going to have to ask you to, maybe take a seat because we found a new largest prime number. And this number is both large and in charge. It is absolutely gargantuan.
Well, I remember a couple years ago when we did our episode Primetime, I think at the end we had a talk about the largest known prime number, didn't we?
We did. And now, of course, this new one is bigger. But before we say how much bigger, what if we take a re-listen to that bit from Primetime?
All right, let me cue that up. Okay, so we've determined that there isn't such a thing as the largest prime, period. But I'll bet there is such a thing as the largest prime that's been discovered to date. And I wonder what that number is.
This biggest one was discovered in 2018. And first of all, let me tell you, the number has more than 24 million digits. In fact, it has exactly 24,862,048 digits.
Oh, yeah, I remember that now. 24 million digits. That largest known prime was an insanely big number.
Yeah, and this one is insanelier, biglier, if I may. This new prime number has 41,024,320 digits. So it's got almost twice as many digits as the previous one.
I can't even get my brain around it. We're not talking about the number 41 million. We're talking about a number with 41 million digits in it. And the difference between those is astronomically huge. I mean, just to give it a sense of scale, picture the difference between the number 100 and a number with 100 digits in it, how much larger that is.
Yeah, I was trying to picture, like, what if you wrote this number down in a book? Obviously, a single piece of paper is nowhere near big enough, but I can't even imagine how many volumes of an encyclopedia would you need to write this number down. I don't even think like Encyclopedia Britannica is big enough.
Yeah, I was just thinking, how long would it take to count to this number? And I have a feeling I don't have enough time on this earth to count to this number.
Yeah, it would have to be like a relay race where as you're rounding the corner and you're like 97 years old, you pass the baton, please keep counting. Like I just don't think you're ever going to get there. It's just too huge.
Yeah, and a number that big, it really leads my brain to one ginormous question, Pete. And it's, how do we even find a prime number that big? What crazy set of steps did the team that found this have to follow to, one, find it, and then two, confirm that it's prime? Do they have to sit there going, well, is it divisible by 2? Nope. Divisible by 3? Nope. Divisible by 5? Nope. I mean, and all the way up? I mean, how do they even confirm that a number like that is prime?
Yeah, that's a super interesting question. We mentioned in prime time when we were discussing the previously known largest prime, we mentioned the fact that it has a particular form. It is what's known as a Mersenne prime.
Oh, yeah. I remember you mentioning Mersenne primes back in that episode. And I recall that they have names that start with the letter M, but I don't remember exactly what Mersenne primes are. Can you remind the listeners and me what they are?
Yeah, in fact, the me from our primetime episode can remind you and me both, along with our listeners. Why don't we take a listen to that? The M stands for Mersenne, a French intellectual Catholic priest named Marin Mersenne, born in, I believe, 1588. And he was interested in prime numbers that could be written in the form 2 to the n minus 1. In other words, prime numbers that were 1 less than a power of 2. So here's something that's interesting. Mersenne was studying these numbers back in the early 1600s. We still don't know if there are infinitely many of them, Mersenne primes. Since he first introduced this idea, we have found exactly 51 of them.
So now I guess we've found 52.
Yeah, this is the 52nd known Mersenne prime, and it's astonishingly large. It has more than 41 million digits. And as we just heard, we don't know if there are infinitely many Mersenne primes or not. However, we've only found 52 of them so far, and these numbers are getting huge. So I don't know. Intuitively, are they going to keep going forever? It's kind of anybody's guess, right?
Yeah. So I feel like listening to that clip sort of started to answer my question. My question was, how do mathematicians go about finding these really large primes? And then you brought up Mersenne numbers. And while not every Mersenne number is prime, they kind of can give mathematicians a bit of a roadmap towards what are some numbers that would be smart to check.
Let's follow the map and see where it leads us. I'm getting a little excited. You're damn right I'm getting excited.
Yeah, I think that's one of the primary reasons that people look at Mersenne numbers is because of this formula, or as you say, this roadmap. So a first thing to know about Mersenne primes is that they are Mersenne numbers that are prime. And for that to happen, the exponent has to also be a prime number. So right away, we can restrict our attention down to prime exponents. So numbers of the form 2 raised to a prime power p minus 1.
So just to bring this way back down into the realm of the numbers that we all use and love every day, that would be like 2 to the third or 2 to the seventh or 2 to the 11th, where the exponent is prime. And then you take that power of 2 and subtract 1 from it to get the Mersenne prime candidate, we'll call it.
Yeah, and it's interesting. You just mentioned a couple of choices for the exponent. You said 3, 7, and 11. Let's just look at each of those. So 2 cubed minus 1. Well, that's 8 minus 1, which is 7, and that happens to be prime, right?
Yeah.
Okay. What about the exponent 7?
Well, 2 to the seventh would be 128. So taking away 1 leaves 127. Is that another Mersenne prime?
It is because, as you can check, 127 happens to be prime. Now, the last choice that you suggested we look at was 11. 2 to the 11th, it turns out, is 2048. Subtract 1, and you get 2047. And you may wonder, is 2047 prime?
Hang on a second, Pete. I'm wondering something. Is 2047 prime?
It's not. You can check. It's equal to 23 times 89.
Okay, so the takeaway here is if you choose a Mersenne number that's derived by taking 2 to a non-prime exponent, like let's say 2 to the fourth, and then take 1 away from that, 2 to the fourth is 16, take away 1, we get 15. That's not prime. And if we raise 2 to any non-prime exponent and take away 1, we're not going to get a prime number. But then even if we raise 2 to a prime exponent and take away 1, we're still not guaranteed to get a new prime, right? I mean, some of the time we will. Those are those Mersenne primes you've been telling us about, but most of the time we still won't.
Right. So to go back to your roadmap analogy, it is a kind of roadmap. It's not a particularly faithful one though, because it would say, well, check prime exponents, right? However, as you say, not every prime exponent leads to a Mersenne prime. So we have some checking to do. There's work. There's real legitimate work required. Even 2 to the prime powers, they may not yield these Mersenne primes that we're looking for.
Okay, but please tell me that that work does not take the form of, all right, let's try dividing it by every single number we can think of.
Fortunately, no. We have some more advanced technology available to us.
We have the technology.
However, let's just put ourselves in the mindset of this team that found this brand new largest Mersenne prime. Now, the exponent that they were working with happens to be 136,279,841. In and of itself, a prime number. So they wanted to take the number 2 and raise it to that power, subtract 1, and then check is the result prime. It turns out the smart thing to do is to start with this process of trial division. Like, let's see if it's divisible by some number of small prime numbers. Let's check 3, let's check 5, 7, 11, 13, and so forth, up to some stopping point. Because if it turns out that this big number that we're looking at is divisible by 3, we don't want to trot out like the world's most advanced technology when all we had to do was check, is it divisible by 3?
I get you. So we're not going to check if it's divisible by every single prime number, but we are going to check a selected set just to make sure we can't just knock this one out of the way quickly and easily and disprove that it's prime by just saying, oh, this is divisible by 3 or this is divisible by 7.
Right, exactly. Now, I should mention that this largest prime was found by an organization called the Great Internet Mersenne Prime Search. And one of the guys on the team named Luc Durant, he's an engineer and a researcher. And these steps that we're describing here, namely starting with trial division, his team started with that. That's sort of part of their playbook.
So I'm assuming that they got this large number and then they started putting it to the test. Is it divisible by 3? It's not. Is it divisible by 5? It's not. How far up do they go in this first step? Do you know?
Well, I think they're balancing out two particular quantities. On the one hand, how much effort is it going to take to continue checking more and more of these factors versus how likely is it that we're going to find a small prime factor. And there is a kind of a formula that you can check to say, here's what our cutoff should be. Beyond this point, we're going to stop checking and we're going to move on to technique number 2.
All right. So what is that second technique?
Well, the second technique is kind of funny sounding because we're going to ask the question, is this number probably prime? And if the answer is right, that's a pretty silly way to express it.
And what do we mean? Is it probably prime?
So you're telling me there's a chance?
Yeah!
I mean, what makes a number more likely to be prime? Are we just saying, well, it's an odd number and it's not divisible by 5, so it's probably prime? Is that what we're talking about?
Well, okay, something not very much like, but like that. There's a different kind of test. And in fact, it's based on a theorem due to Fermat, who we have talked about before. In fact, it's called Fermat's little theorem. And there is a particular application, an iterated application of Fermat's little theorem that allows us to say with fairly high confidence that this number could be a prime. So the idea is to apply Fermat's little theorem to rule out composite numbers. And the more applications of this test, the more likely it is that we've got a prime number, but we won't know for sure. We might know with 99% confidence that it is likely to be prime, but that's about as far as we're going to get using this approach.
So to make sure I understand what you're saying, our first approach is to throw some small primes at it and see if it's divisible. If it's not, we move on to this second technique, which uses Fermat's little theorem to determine if it's probably prime. If we determine that it's not probably prime, does that mean it's definitely not prime? Or does that just mean it's not probably prime?
Yeah. So this test can give false positives, but it can never give false negatives. So if it fails this test, then we know automatically that the number is composite. No prime number will fail this test. Every prime number will pass this test. However, some composite numbers will pass this test. So it may turn out that we have a probable prime that is not an actual prime. Those cases are rare. There's not a ton of them, but they can happen. So we use this test to rule out numbers that are definitely composite.
Okay, what percentage of numbers that pass this test ultimately end up being prime?
Oh, most of them. It depends on exactly how the test is set up and how many times it is run, because there's some fiddly parameters that you can play around with. But essentially, 99% of the numbers that pass this test will turn out to be prime.
Okay, so let's say we've got some huge number, like this new Mersenne prime that was just recently discovered, and we've done technique 1 and we haven't found any small primes that divide into it evenly. We've gone on to the probably prime test and it passed that too. So now this number is pretty likely to be prime, right?
There's a great chance of that, Nick McBee.
At this point, we know we've got like a 99% chance, but we're still not 100% certain. What do we do next?
So when we get to that situation, we run a final test, which is known as the Lucas-Lehmer test. And this will pin down for sure whether or not the number is prime.
And I'm going to stop you there and ask a question. Is the reason that we do the probably prime test first because it's a lot quicker and easier than having to do this Lucas-Lehmer test, which comes third? Like, why not just jump to the Lucas-Lehmer test if it's going to give us a more definitive answer?
Yeah, it's exactly like you say. The probably prime test is faster to run and more effective at ruling out composite numbers. So the Lucas-Lehmer test will reveal whether or not the number is prime, but it's more costly. And so we want to know before we embark upon it, we want to know, do we have a really strong likelihood that the number we're looking at is prime?
Okay, so we've got these 3 techniques of increasing complexity. Would it be okay, Pete, if we kind of took a step back, circled back around, and maybe chose a much, much smaller and more approachable number to sort of put to these 3 tests and see how they play out?
Yeah, sure. I think, yeah, definitely. Let's give it a shot.
Is there a particular number that you think would be a good candidate for us to try this with?
Yeah, let's try it with 2 raised to the 5th power minus 1. So now that happens to be 31. And pretty easily, we know that this number is prime.
Spoiler alert, Pete. Spoiler alert.
Sorry, didn't mean to blow that one. So if we start with 31, listeners either already know that it's prime, or if they don't, that's great. They'll go along on this ride and this will be a big reveal for them. We're in the situation where we've taken 2 and raised it to a prime power. 5 is the prime exponent. So 2 to the 5th, which is 32, and we've subtracted 1. We have 31. We want to know, is this number prime? So let's go down the line.
Okay, so the first thing we're going to do is we're going to choose some small primes and check to see if 31 is divisible by them.
Right. So we don't have to check 2 because every Mersenne number is odd, right? It's 1 less than a power of 2, which is even, minus 1, therefore it's odd. So we wouldn't have to check 2.
All right, that makes sense. So let's check 3. Is 31 divisible by 3? We can tell that it's not. 30 is divisible by 3. It's 3 times 10. 31 is just 1 more, so it's obviously not divisible by 3.
Okay, let's check 5.
All right. By the same token, we know that 30 is divisible by 5. 31, being just 1 more, can't be also divisible by 5, so 5 is ruled out.
Right. So what should we do next?
Well, we could check 7.
Right. Now, in fact, we don't even have to check 7.
Why not?
Well, because 7 is larger than the square root of 31. I don't know what that is off the top of my head. Don't know much about algebra. But I know that it's less than 6 because 6 squared is 36, already too big. So when we're doing primality testing like this with actual division, we only need to check the prime numbers up to the square root of the candidate. So in this particular case, 5 is the final prime that we need to check.
So if none of the prime numbers under the square root of 31 can be divided evenly into 31, then none of the prime numbers at all are going to divide evenly into 31 because they would need some kind of multiplicative pair to multiply with them that's under the square root, correct?
Yeah, exactly. If you've got 2 numbers that multiply together to produce the candidate number, unless you happen to be looking directly at the square root itself, like 6 times 6, one of the numbers will be less than the square root and the other number will be greater than. And so it's always that pairing up that allows you to call it quits when you get up to the square root.
All right, that makes perfect sense. So since 31 is not divisible by 2, 3, or 5, we actually at this point know that it's prime. We don't even have to go on to techniques 2 or 3, but that's only because 31 is such a small and friendly number. If we were dealing with a number with 41 million digits, this would not be so obvious. So let's go on to the second technique and see how that would work with 31.
Yeah, we'll pretend that like, man, we just checked a whole bunch of prime numbers. None of them were factors of our candidate. So we just don't know at this point if it's prime or not. So we got to go on to something else. Let's move on to this probably prime test.
Okay.
So now I want to tell you about Fermat's little theorem.
You know, Fermat was the first person to actually go on the record to say that size doesn't matter.
It's true. And this theorem is so little, I think you actually need like a monocle to see it. It's really tiny.
All right, hang on. I've got a monocle around here somewhere.
Okay, so let me explain how this is supposed to work. We start with the candidate number that we want to test for primality. And to do that, we're going to perform some operations that'll probably remind you of the modular arithmetic we talked about in our episode Key Ideas.
Oh, yeah, I remember modular arithmetic. It's the math used in encryption.
Right. So what we're going to do now is this. We'll pick a base number that's less than our prime candidate. Then we'll subtract 1 from our prime candidate and raise this base number to that power.
Okay.
And then finally, we'll divide our prime candidate into the result and check what the remainder is.
Okay, wait, what? This is all getting away from me.
You know what? Let's try it out with some actual numbers, and I think it'll make more sense.
Okay, so let's continue with 31.
We could do that, and I think we should in a minute. But for now, let's start with an even smaller and easier number. Let's use 5 as our candidate for this first try.
Sounds good. So we're trying to find out if 5 is probably prime.
Right. Now, we're going to need a few other quantities here. We'll need that base number, which I'll let you choose in a second. And we'll also need to figure out the power we're going to raise that base number to. And that has to be one less than the candidate number.
Gotcha. So if our candidate number is 5, then we'll be raising that base number to the 4th power.
Exactly. So go ahead and choose a base number, any number less than our candidate number of 5.
Well, we already have 4 as the exponent, so let's go with 3 for the base number.
Perfect. So to get started, we're going to take your base number and raise it to the 4th power. What does that give you?
3 raised to the 4th power is 81.
It's 81. All right. Now, remember that 5 that was our prime number? If you divide 5 into 81, what's the remainder?
Well, 5 is going to divide evenly into 80, so the remainder will be just 1.
Exactly. The remainder is 1. Okay, let's just do one other example, and then we'll see what happens. Let's try 2. So you had picked 3. Let's try 2. Okay, what is 2
All right.
raised to the 4th power?
2 raised to the 4th power is just 16.
All right, divide 16 by 5. Tell me what the remainder is.
Well, 5 times 3 is 15. Hey, the remainder's 1 again. Is that a coincidence, or is there some pattern that we're revealing here?
We're definitely revealing a pattern, and Fermat noticed this pattern. And what we're doing, every time we divide 5 in and look for the remainder, this is the part I mentioned a minute ago that might remind you of modular arithmetic. So it's like we're doing arithmetic on a clock where we've only got 5 hours on the face, right?
Yeah, it does remind me of that. It's like how many times you go around and then how many left over. What's the modulus?
And if the modulus is prime, and you perform this exponentiating that we're doing, where we raise it to the power that's 1 less than that prime, that's why we were raising it to the 4th power, you will always wrap around the clock and go just 1 unit past. It'll always be 1 o'clock.
All right. So how do we apply this to trying to figure out if 31 is prime?
Right. So in this case, we're going to set the modulus P equal to 31. And that's the number we're going to use when we do this division and look for the remainder. Now, if 31 is prime, when we do this process, every remainder should be equal to 1. So in our previous example, we picked a number that was less than the modulus. First, we picked 3, then we picked 2, and we ran through the operation. We can do the same thing here.
All right, let's start with 2 again, because I have a feeling these numbers are going to get really big.
Yeah, we have to raise these numbers to the 30th power now, right? 1 less than 31 is 30. That's our exponent. So I'm just going to navigate myself over to Google, and I'm going to do a little calculation there. So I'm going to raise 2 to the 30th power. And if I do that, it doesn't really matter, but I'll just tell you, what did I get? I ended up with something slightly bigger than a billion. 1,073,741,824. We don't really care about that number.
Okay, and now we're going to divide that by 31 to see if we get a remainder of 1.
Exactly. And if I do that, the quotient is, it looks like the quotient, again, these numbers aren't super important, but it goes in 34 million times, a little more than that, 34,636,833, but it leaves a little bit left over. And if I ask what the remainder is using that quotient, lo and behold, I end up with 1.
All right, so if we had gotten anything other than 1, that would rule out the possibility of 31 being prime. The fact that we got a remainder of 1 tells us we're still on track. It still could be. So now we should try 3 instead of 2 and see if we get another remainder of 1.
Yeah, let's try 3 and see if we blow up my computer or if it can actually handle numbers that big. Okay, so 3 to the 30th. Yeah, it's 2 times 10 to the 14th power. It's got some other digits in there, but it's a very big number. However, 3 to the 30th, if I divide by 31 and look for the remainder, once again, I get 1. Google tells me the remainder is 1. Of course, Fermat already told us the answer was one. He didn't have to get out any kind of computer. He just knew the answer is going to be one, right?
And none of our listeners should be surprised that that remainder is one, because in this case, spoiler alert, we're not really trying to figure out if 31 is prime. We already know 31 is prime. So whatever number we choose to use as the generator, whether it's 2, 3, 7, 15, whatever, they're all going to give us a remainder of one in this case.
They are. Now, if the modulus were not prime, if it were a composite number, then we would expect to see remainders that are different from one. Every time we get a remainder of one, however, it raises our confidence that the modulus that we're looking at is actually a prime number.
So when Luke Durant and his team were testing this 41 million digit number, they probably did something like what we're doing here, but on a much larger scale. And every time they got a remainder of one, it was like cheers all around the nerd room, right? I mean, yes, yes. I can hear all the little nerds right now with their yips and their yays, and everybody's pushing their glasses back up on their noses.
Yes, that's exactly right.
And I just want to be clear that we are not really poking fun at nerds in any way. I think we proudly consider ourselves amongst their number.
Definitely. And I myself am supposed to be wearing glasses and haven't been. So shame on me. I need something to push up on my nose. So I'm overdue for that.
All right. So we just checked 2 and 3. We got remainders of 1 for both. How many, technically, if we didn't know 31 was prime, would we want to check?
Yeah, conceivably, we could go all the way up to 30, right? 2, 3, 4, 5, 6, 7, all the way up to 30. That would be very expensive if your modulus has 41 million digits in it. So we clearly are not going to check every number, right? That's way out of our league. So we need to use some kind of heuristic. And this is all done in distributed computers in the cloud. And there's a lot of computational power that goes into carrying out these tests. But again, there is some sort of cutoff point, and they go, boy, we just checked, say, well, in the case of 31, maybe we check 5 or 6 numbers, maybe not even that many. I'm not sure. But at some point you go, boy, we just got a lot of ones. I think we're going to say this number is probably prime. And so we would defer to some heuristic, and then we would proceed to the next step,
which is the Lucas-Lehmer test.
Yeah, the Lucas-Lehmer test is actually really interesting. And the first thing to know about it is it only applies to Mersenne numbers. So you can't take some arbitrary number and use this test to determine if it's prime. It's really tailored to Mersenne numbers.
Okay, and I'm assuming that unlike the test for probably prime that we just did, this one will actually give a definitive answer if the number is prime or not.
Yeah, and what's interesting about this is that we're talking earlier about the number 31 and whether or not it's prime. What we did was we tried a bunch of divisors and we said, is it divisible by 2? No. Is it divisible by 3?
No again. No. 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 No.
And we went up until we'd gotten to the square root of the number. We verified primality because we saw that none of those primes divided into it. Contrast that with a number like 51. If we wanted to know if 51 was prime, we would perform this same division test, and we would find that, lo and behold, it is not prime. It's equal to 3 times 17. So using that kind of division technique, when we determine that a number is not prime, we do so by explicitly factoring it.
Okay, that makes sense. And is that going to be a part of this Lucas-Lehmer test?
It is not. This test won't give us any insight into a factorization of the number. All it can tell us is yes or no, the number is or isn't prime. We get no information about divisibility in the case that it's not.
Well, that's really interesting because whether or not a number is prime really has to do with its factors. And it's kind of intriguing to me that this test for primeness doesn't involve factoring it. So how does it work?
First, we're going to build out a sequence of numbers, and that sequence will be the same no matter what our prime candidate is. And we make this sequence as follows. We start with a seed value, in this case, the number 4. We square it and subtract 2. That gives us the first term in our sequence. Then we square that and subtract 2 to get the second term. And we keep going just like that, squaring each term and subtracting 2 to get the next one.
Okay, and what are we going to do with this sequence?
Well, remarkably, we only need to use one of the terms in this sequence to perform the Lucas-Lehmer test. And our prime candidate, the Mersenne number that we're looking at, it tells us which term to use.
Oh, that's interesting. How does it do that?
Well, we look at the exponent that 2 was raised to in order to create that particular Mersenne number. Subtract 2 from it, and that tells us which term in the sequence we should look at.
Wow, I hesitate to ask this, but then what do we do with that term once we know which one we need?
We divide our prime candidate into it, of course.
We divide the prime candidate into it. Can we just do an example with actual numbers again? I think that'll help it make more sense.
Sure, let's stick with the number 31 and apply this test to see if we can confirm that it's prime.
Perfect. So how do we start?
Okay, first, let's generate that sequence I mentioned and figure out which term we'll look at. We're going to think of the number 4 as a seed, as an initial starting point, and the first term in the sequence we obtain by squaring 4 and subtracting 2. So in this case, what do we get?
Well, if we square 4, we get 16, and then subtract 2 brings us back down to 14.
Great, that's the first term in our sequence. Now, we're going to repeat that process of squaring and subtracting 2 to get the second term in the sequence. So what does that give us?
All right, so now we're squaring 14 and then subtracting 2?
That's right.
All right, so 14 squared is 196. Take away 2, and that leaves 194.
Perfect. Okay, now to get the third term in the sequence, we would repeat the process, square 194 and subtract 2. Now, I'm not going to expect you to know 194 squared off the top of your head.
Okay, ye of little faith, I happen to know that 194 squared is 37,636.
Do you have your table of squares memorized out to like 200, or what's the deal?
No, man, I'm a third grade teacher. I got to know these things. Kids come up with questions.
Okay, fair enough. All right. So the third term in the sequence ends up as 37,634 because we have to subtract 2, right?
Right, makes sense.
Now, we could continue on and on and on. This sequence can be extended out however far we'd like to go. But for our current purposes, we can stop right here.
Because we've gotten to the term we need?
Exactly.
And remind me how we know which one that is?
So now the Mersenne number that we're looking at, whose primality we're trying to establish, is the number 31, right?
Right.
And what is the prime exponent that is associated to that Mersenne number?
Well, does that mean 5 because that Mersenne number was 2 to the 5th minus 1?
That's right. The prime exponent in this case is p equals 5. Now, subtracting 2 from that, this is part of the test. We have to subtract 2 from the prime exponent. And in this case, we get, drum roll, please.
3.
Yeah, well done. So, all right, that 3, p minus 2 equals 3, that tells us which term in the sequence to look at. So in this case, we can look at term 3, which is 37,634.
All right, and what do we do when we're looking at it?
We ask, does our candidate Mersenne number 31 divide evenly into 37,634?
So instead of figuring out a factor of 31, we're figuring out if 31 is a factor of this much larger number. And let's see. It looks like it is. 31 times 1,214 would give us that value.
That's right. This third term in the sequence, 37,634, can be factored with 31 as a divisor. This means that 31 is prime.
It does?
It does.
But how in the world does that work, Pete? Like I just said, we're not figuring out if 31 has any factors other than itself and 1. We're just figuring out that it's a factor of this other number.
That's right.
So how does that confirm that it's prime?
Well, to really get a handle on that, you would have to take a look at a proof of the Lucas-Lehmer test. But essentially, the proof works by contradiction.
Oh, okay. I remember talking about proof by contradiction in our episode all about proofs. It was the strategy that we would use to make an assumption. And then if by logically following through on that assumption, you lead to a contradiction, you know that your initial assumption couldn't be true.
That's right. And that same principle is at play here. In this case, the assumption that we make is that our Mersenne number is in fact not prime. It divides the term in the sequence, but it nonetheless is not prime. And using some group theory and some other advanced mathematics, you can derive a contradiction. Essentially, you end up showing that a certain number is actually less than itself. And in fact, that can't possibly happen.
So by showing that that can't happen, it means that this number can't be composite.
That's right. And so therefore it must be prime. And in this case, since 37,634 is evenly divisible by our prime candidate of 31, it means that 31 must be prime. It's that simple.
So if it's that simple, why do we bother with all the other tests first? Why don't we just do this one? It seems so quick and easy.
Yes, it was. But remember, the prime exponent in this case was 5. When we subtracted 2, it meant that our stopping point was 3. We only had to go 3 terms into the sequence. And even that third term, let's look at how big it is. It's more than 37,000, right? That's term number 3. Imagine, though, that we're going to square 37,634 and subtract 2 from it, okay? That gives us the fourth term of the sequence. For this newest big prime that was found in October, we would need to calculate 136,279,839 terms of this sequence.
And I can only imagine how big that term is going to be. It's going to leave this 41 million digit number in the dust, isn't it?
It would. Now, there are techniques that we can use to sort of simplify and to take shortcuts, but effectively, what the test is asking us to do is to go out 136 million, some spots in this sequence, and ask, does the number with 41,024,320 digits in it happen to divide this term in the sequence that is 136 million slots down the line?
Okay, I get your point. It's not as quick and easy as it seems. But I'm still assuming that Luke Durant and his team had to go ahead and do this. That's how they finally confirmed this new Mersenne prime, right?
Yeah. And now, again, they would have used additional computational shortcuts, right? So you actually, at every step in computing the sequence, you actually can perform some reductions as you go, namely using modular arithmetic. But even that is expensive. So in terms of computational cost, squaring a number is fairly expensive. And computing a modulus, computing a remainder, is also expensive. So every step of the way is a costly, potentially time-intensive step. So they would have looked for shortcuts, but when all is said and done, this is effectively what they had to do.
That must have taken an enormous amount of time. I mean, yes, it was quick and easy to do it with a number like 31, but you're right. With a number with 41 million digits in it, this is a bear of an operation.
Yeah, I would not recommend asking your third grade students to do this kind of arithmetic by hand.
Oh, no. I would get one of the fifth grade teachers to put their class on it.
That's really smart. You just bootstrap your way up, right? I love it. That's perfect.
That would be pretty challenging for the third graders, though. And thinking about pretty challenging and also thinking about prime numbers, I was thinking it would be kind of fun to give our listeners a prime number puzzle to chew on before our next episode. What do you think of that, Pete?
Ooh, I think that's great because I happen to have a very natural puzzle in mind already.
So do I. I wonder if we're thinking of the same one.
Well, are you thinking of having listeners find the 53rd Mersenne prime?
No, that is not what I was thinking. Our next episode comes out in a few weeks, Pete. You said this latest Mersenne prime took 6 years to find. I mean, how much time do you think our listeners have between now and our next episode?
Well, they better get cracking then. That's all I can say.
No. All right, here's the puzzle I was thinking of, Math Club. If you take all of the unique digits from 0 to 9 and rearrange them into as many different 10-digit numbers as you can, there are 3,250,000 265,920 different 10-digit numbers that each use all 10 of the digits from 0 to 9. Here's the puzzle. How many of these numbers are prime?
Oh, I like it. So just quickly to clarify, 0 will not appear as the first digit of one of these numbers, right?
Right. If 0 came first, it would be a 9-digit number, not a 10-digit number, effectively. So yeah, that's what I was thinking.
Perfect. Okay. So, well, I think that's interesting. And I think listeners, well, they should still get cracking because that's a lot of numbers to go through.
It is. It is. And we will give a shout out to the first person to solve it and let us know their answer on our next episode. Speaking of which, Pete, why don't you tell people how they can reach out to us to submit their puzzle answer or for any other reason?
You betcha. As always, Math Club, you can leave us a voice message on our SpeakPipe account. The address is speakpipe.com/Math Club Podcast. You can also reach out to us on Twitter. Our handle is @Math Club Podcast. Or why not send us an email? Our address is mathclubpodcast@gmail.com.
All right. That was a fun one, Pete. I feel like I am primed and ready to go.
Alrighty there, Dad Joke. We will catch up with you and everyone else in our next episode.
Bye, Math Club.